This video deals with a special kind of a function that we deal with a lot in linear algebra, and it looks like this. Let me start with the definition of what it is. It's called a linear transformation. Now, linear transformation from a vector space V to another vector space W is a function T. We use capital letters for these things. The function T, where T has the following properties. So if I have, here's the first property, if I have two vectors in V, say U and V, then T is going to, since it's a function from V into W, it's going to send these, or this sum, into some sort of a vector over in W. However, the rule that we must abide by is that I can break this into this kind of a sum. This is not something you can do with many functions, where I can break it up like that. And the other one is if I take T of a scalar multiple of a vector, I can pull the scalar multiple out front. So keep this in mind. T of U and T of V are in W. T of U is in W. Since W is a vector space, C times it is also in W. The notation we use is the following. We usually write T full colon V arrow W. That's just usually the notation we use. This way you can see V is the domain, W contains the range. Now, I want you to notice something about this definition. These two rules are meant to preserve closure under vector addition and scalar multiplication. As you can see, these specifically look like they were made for vector spaces, don't they? It takes a sum of two vectors and sends it into W where it's a sum of two vectors. It takes a scalar multiple of a vector and sends it to a scalar multiple of a vector in W. So keep that in mind. Whenever you see something like this, T of U is in W. Just keep that in mind. You got to keeping track of when you're in V and when you're in W can be a little bit complicated sometimes. So just always keep that in mind, that it's a function from V into W. Another note, V is the domain, and the following set where I have T of U such that U is in V is the range. Another definition. Let T from V into W be a linear transformation the kernel of T is the set of all x in V such that T of x equals the 0 vector. And remember, this 0 vector is in W, so keep that in mind. Sometimes I might put a little W at the bottom of the 0 to emphasize the fact that that vector is in W. So basically, these are all the items in the domain that get sent to 0, is basically all that this is. And it's referred to as the kernel. Now let me give examples of some linear transformations. Probably the best one, the most useful one to us, is the following. I'm going to pick an M by N matrix A, and we can define a function T from, in this case here, remember that A is an M by N matrix. What that means is its domain is R to the M, and its domain is R to the N, and its range is R to the M. So it is a function from R to the N into R to the M, defined by, we can define this function T from by, I'll just use the word by, T of x. So you can see this makes sense. A has n columns, and x will have n rows since the domain is R to the n. Now this function here is actually a linear transformation. The way we check that is we try those two closure properties and see if they hold for this. So, for example, in part 1, if U and V are in R to the N, then T of U plus V equals A times U plus V. We already know matrix multiplication is distributive. And then if I finish this off, that A times U is equal to T of U, and the A of V is equal to T of V. So it has the closure property under addition. The second one is scalar multiplication. So this time I'm going to let, if C is a real number and U is in R to the N, T times CU is equal to A times CU. I can factor the C out front, so it's C times AU, which is C times T of U. So it preserves that multiplicative closure property as well. So this is probably the most famous of all the linear transformations. We'll be using it a lot before the semester is out. Now I want you to notice something here. The range of T, that's this T up here, the range of that T is the following. I don't know if I want to give it a letter or not, but I'll write down what the set is. That would be A of x such that x is in R to the N. But we already know what this is. This is the column space of A. So the range is simply the column space here. And what's nice about that is you can see that we already know the column space is a subspace of, well, I guess in this case, r to the m. Because, remember, it was, what was it? It was generated. I don't want to say use the word generated. It was the span of a collection of vectors, in particular the column vectors. Now, with this, let's do a theorem that might provide a little more theoretical insight. I don't want you to forget this. Column of A is in the range. So it is, and it's not it's not in, that's the wrong thing to do. It is actually a subset of the range. Or it is the range. It's a subset of r to the m. Let me do a theorem. As before, we'll let T from V to W be a linear transformation. The kernel of T is a subspace of V, and we probably, and I've seen various things for it, but for the proof of this, I'm just going to refer to K as the kernel. So I'm going to let K equal the kernel of T. So we know that anything that's in K, T of that is going to be the zero vector in W. So let's start with the two properties that we have. So in one, I'm going to let's say we have U in V, R in V. I want to show that their sum is also in K. So let U and V be in K. Then if I do T of U plus V, this equals T of U plus T of V because of the closure property of addition. And I know that this thing here, this T of U, is the zero vector in W. I'll put a little W down there. This one here, since it's in the kernel, is also the zero vector in W. So when you add them together, well, 0 plus 0 is 0. So we have that property there. I have the sum, U plus V, is in the kernel. And the second one was scalar multiplication. So I'm going to let C be a real number, and I'm going to let U be in the kernel. So when I do T of CU, well, according to the linear transformation rule, I can pull the C out front, and I have T of U. But T of U is equal to the zero vector in W. And since W is a vector space, this equals the zero vector in W. Now these two rules are the closure properties for being a subspace. There was one more property which I put last because it doesn't go with the flow just yet. But the zero vector in V, does it equal the zero vector in W, the T of that is? Well, I know within V, 0 is the same as 0 plus 0. And then I can break it apart. T of 0 plus T of 0. Now on the other side, I'm going to put my T of 0. Now keep in mind that all these T of 0s, these are all in the vector space W. So all this, any kind of things I'm doing out with these T's in front of here are in W. So within W, I'm going to subtract T of 0V from both sides of this equation. And what I end up with, since I'm doing this subtraction within W, and I'm taking some vector minus itself within W, this is the 0 vector inside of W. Same over here. I don't know what it is yet, but the same thing happens here. I get the 0 vector in W. Now, the 0 vector in W plus a vector in W is just that vector, because the 0 vector is the additive identity. So this on the right is T of 0v, and on the left I have 0w. So in fact, the 0 vector in V is also in the kernel. So those three things show me that K is a subspace of V. Here's a little bit of a different flavor of example here. Let F and G be continuous functions on a closed interval AB. And this actually has a notation associated with it. The set of all such functions is called capital C sub, actually I don't think it's a sub, it is just C closed interval AB. So that is a set there of all the continuous functions defined on AB. And of course, these continuous functions, they are from the real numbers into the set of real numbers. So the domain and range are in the real numbers. So in any case, these kind of functions, these kind of continuous functions, actually forms a subspace. CAB is a subspace of the set of all functions from R, from the reals to the reals. I have to take my word for it that the set of all functions actually is a vector space. The set of continuous functions is a subspace. You can see that by looking at the three axioms. The function f of x equals 0, just the 0 function, well, that is a continuous function, so it is in CAB. And then if I have f of x and g of x as continuous functions, then you know, well, you should know from calculus that their sum is also a continuous function. And last one, this shouldn't be so hard at all. If you have a real number and you have a function in CAB, another result from calculus is that C times f of x is in C of AB. Okay, so it's a subspace. That's not really important for what I wanted to do. What I want to do is to define a function t from CAB into the real numbers by the following rule. I'm going to take a function from the continuous functions, and it's going to equal the integral from a to b of f of x dx. And you ought to know a definite integral is will output real values, so that's why this is going into the reals. Alright, anyways, let's go ahead and check the three axioms and see, well, to be a later transformation, I only need to check two things. That it preserves sums and it preserves scalar multiples. So let's start with t of f plus g. And that's defined as the integral from a to b, f plus g of x dx. This notation is one that you should recognize. F plus g as a function itself can be broken up into f of x plus g of x. And one of the rules of the integral is that I can break this up into a sum of integrals. You may have remembered when you were taking calculus, they referred to linearity properties of the integral. Well, they were talking about this. And of course, this first integral here, that's equal to t of f. And the second integral is equal to t of g. So there's part one. The second one is that it preserves the closure with respect to scalar multiplication. So if I have c times f, then that integral will go from a to b of c times f of x dx. And once again, you know from integrals that you can pull constants out front. And so that equals c times t of f. So it satisfies the two properties that we need. T is a linear transformation. Another example, let's define t from p sub n to r to the n. By the way, this is a notational thing. I have in the past been using p raised to the n to be the set of all polynomials of degree less than or equal to n. While it doesn't hurt anything to use that notation, the notation actually is p sub n. Apparently I haven't been keeping up in my readings. But anyways, p to n is the set of all polynomials of degree less than or equal to n. Alright, so anyways, here's my definition. I'm going to take a polynomial, so p of t. So remember, the vectors in this particular set are polynomials, so that's why I'm using that here. And the definition I'm going to use is the following. In the first coordinate, remember, r to the n are vectors that have n coordinates. So what I'm going to do is put p of 0 in the first spot, p of 1 into the second spot, all the way down until I get to the end. I'll put p of n. That means that I'm evaluating the polynomial for x equal to 0, or well, I think we use t, for t equal to 0 here. Then I'm evaluating the polynomial for t equal to 1, all the way down until we get to the end. I'm evaluating the polynomial for t equals n. It's kind of funny because then you'll have in the last part of it, when you plug this in, you'll have n raised to the nth power. Anyways, let's take a look. If I have two polynomials, p of t and q of t, according to this rule, I'm going to send that to p of 0 plus q of 0, p of 1 plus q of 1, all the way down until I get to p of n plus q of n. Well, it probably doesn't take any guesswork on your part to see that I'm going to break this into p of 0, p of 1, all the way down until I get to p of n, plus q of 0, q of 1, all the way until I get to q of n. And of course, this first vector is equal to t of p of t, and the second vector is equal to t of q of t. So there's the first part that I need to prove to show that it's a linear transformation. The next is closure under scalar multiplication. So if I have a scalar times a polynomial, and I send it into r to the n, it will be cp of 0, cp of 1, all the way down until we get to cp of n. Then I can factor the c out. And of course, that is equal to c times t of